Good morning, everyone. Thank you for joining us today and welcome to Production Modeling Corporation's web presentation. Today's topic is critical role of manufacturing simulation in your system's performance. This will be presented by Edward Williams, a senior technical specialist at PMC. On a housekeeping note, we will be muting all phones and microphones throughout the presentation, limiting any background noise. And please, if you have any questions, please type those into the Q&A section on the bottom of your screen, and we will answer your questions at the end of the presentation. To start, I'd like to do a brief introduction to PMC. Since 1979, PMC has helped over 700 companies by completing more than 7,000 performance-enhancing initiatives worldwide. It is our commitment to excellence that has brought us to the point we are the largest independent industrial engineering services firm in North America. Today's session will focus on simulation, but here's a sampling of the other services that PMC offers. Now, I'd like to turn things over to Ed to begin our presentation, using simulation to improve your system's performance. Ed, take it away.
Thank you, Brian. Ed Williams here, the old gray one. I'm 78 and I've been doing simulation work for about half of that time. And simulation is an enormous help with a great many business decisions. Some of the most common are listed on this slide. Many of them apply primarily to manufacturing and warehousing. Others, like staffing levels, maintenance, inventory policies, can apply all across the board. And with all these decisions to make, businesses certainly need a good decision-making analytical tool set to contribute right to the bottom line. And there's so many objectives that go along with those decisions. Equipment and workers are expensive, so we'd like to have them have high utilization. Whether our customers are the things we're manufacturing or the parcels we're shipping or the people we're serving, we'd like the waiting times and the waiting lines to be short. And we'd like to keep our inventory low because inventory ties up cash and the space to keep it ties up cash. And yet we'd like never, well, almost never, to have a stock out. And we'd like to have our downtimes, I suppose a few are inevitable, but we'd like them to be rare and short. And so many of those worthy objectives work at opposites. They are trade-offs. I'd like low inventory, but I don't like it to go down to zero. That's a stock out. I'd like my equipment and workers, for that matter, utilization to be high, because they represent an expensive cost of the equipment, cost of the workers, and yet I'd like my queues, both length of the queue and length of the time in queue, to be short. They work as opposites. I'd like to keep my personnel costs down, but I'd like to get work in and out the door quickly. Here's low inventory again. I may have inventory of many different parts, for example. And if I keep my changeover time low, I don't change over very often, but then I build a high inventory of whatever I'm making, like a part type, until I change over. I'd like my downtime to be low, but maintenance costs low also. And low equipment and personnel cost are frequently at odds with the high throughput I'd like. So what's a manager to do? Open up the arsenal. Here at PMC, we have a huge arsenal of analytical tools that can help business. Simulation is just one of those, the one we're concentrating on today. It's one of the most valuable tools in the arsenal, and it is more valuable when it is used synergistically with other tools in the arsenal, like Six Sigma, value stream mapping, ergonomic analysis, and so forth. Simulation is at its best when it's working with other tools. Now, more on simulation in particular. Here are some of these methods of attack. In no particular order, other than since this webinar is about simulation, I put it at the top. But simulation works in conjunction with and synergistically with all of these statistical methods, the other 7 things listed on this slide. One of the great virtues of simulation is that it can analyze systems under severe conditions of uncertainty and randomness, which many basic arithmetic methods, like a static Excel formula in a spreadsheet, cannot do. And whenever you have randomness and stochastic variation, statistics is not far behind. So any simulation project needs a very good statistician in the wings to do these other methods of statistical analysis of both the input to the simulation and the output provided by the simulation to translate those numbers into the best business decision for you. And an accurate simulation model that directly contributes to the bottom line of your enterprise and significantly contributes to your customer satisfaction, which goes right to the bottom line. Such a model is built on 3 pillars. First, the model has to be correct. It has to model the right problem in the right conceptual way, and the computer must be correctly told what that model is. The input data must be accurate in themselves and must be accorded accurate statistical analysis, such as the correct probability distribution to use to properly model stochastic input data, such as random cycle times, randomly occurring downtimes, random customer demand, and so forth. And the experimentation with the model to produce its output, if the simulation is what we call steady state, the experimentation must account for the initial transient or warm-up period, the potential solution space of alternatives that your management is considering has to be examined thoroughly. The sensitivity of the results has to be examined carefully. In other words, if a particular input to the model changes a little, will the performance of the system being modeled change a little or a lot? And under the heading of design of experiments, the experimental design use must be appropriate, such as factorial, fractional factorial, Box-Banken, Latin square, etc., to drop a few names that the statistician will be familiar with. And be cautious and aware, a simulation model's quality is equal to the lowest of all of these three. Those are the three pillars. They all have to be strong. And sensitivity analysis, it's very easily done on the computer. Very convenient, very quick. And as I mentioned, does a small change in some input variable, and frequently that is arrival rate of your orders or customers. We often do simulation projects for businesses planning to expand. Will that lead to a small change or a large change in Y, the output variable? And Y represents typically some performance metric of importance to you, like amount of throughput, average queue length, average waiting time in queue, utilization of an expensive machine, and so forth. And where simulation really shines is we need improvement. How do we get it? We have only a limited amount of money and time, by the way, not just $X, but time. Where should we put it? There's 5 alternatives here and then a bunch of question marks. And indeed, one of the first questions we ask a new client is, do the 5 that are listed here apply? They often do. They're often likely alternatives. And help us make this list bigger so we know what our simulation analysis should look at. This list of 5 and then an open end, we often persuade a client to expand this list to 10 or 15 or 20. That expansion is best done before the simulation modeling begins. And a marvelous power of simulation, which not all analytical methods have, is exploring interactions. On the previous slide, we just looked at, here were several possibilities with a strong hint that we're eager to look at more of them. Do they interact? It may be that the new faster machine by itself produces hardly any improvement. And it may be that investing in one more worker produces hardly any improvement. And yet it may be that investing in both produces a very significant, worthwhile improvement, well worth making both investments. That is a correlation or a synergy. And simulation work, modeling a lot of alternatives side by side, and by a lot, I frequently mean 20 or 30 or 40, plus the correct output analysis, which when you get that many is very often a carefully chosen design of experiments design, can find that synergy. And on the computer, you can effectively explore a great many possibilities. Whoops, skipped one. So first, a very tiny demo. Here's a little tiny simulation model, perhaps of interest as someone familiar with this particular software package. It's called Simio. It's one of a dozen we use here at PMC, 5 of which I know thoroughly myself. All our engineers are required to know at least 3 of them, so we have a deep bench. And the issue undertaken This is like under a magnifying glass. The key issue in several large projects we've done recently. We have arrivals arriving faster than the main machine can handle them. When the lineup gets too long, we send them to the backup machine, which may need another worker or be more expensive to run or whatever. So we say, well, when this line gets too long, we'll send parts here also. And that can be animated. The animation takes almost no incremental effort beyond the simulation. That's one of the advantages of simulation software. And eventually this line will get long enough that work will go to the backup machine. I just told it, speed up the animation a little bit more. That's readily under control. And it won't be too long before we see a part go to the backup machine. There's the first occurrence. I told the model, put that on the screen in case of interest. The model can be fast forwarded. And even better yet, well, you heard me say, well, when that lineup with the main machine gets too long, send work to the backup machine. Well, how long is too long? Now this proposes when the line gets longer than 5, we'll send it to the backup machine. And when the main machine catches up so the line is no more than 3, we'll stop use of the backup machine for the time being. Well, that's one possibility, but here are some other possibilities. We'll run and compare. Throughput is likely a key performance metric. Did it make much difference? That would be a matter of perhaps no investment at all, but simply setting policy. And we have a very quick comparison. It didn't make too much difference. That small looking difference may be very important. So there's an example of a very tiny model, perhaps of interest. It took me about 25 minutes, not quite half an hour, to build that model. It represents a microcosm of a large system and a typical issue within a large system. Several of our different clients had that type of issue to consider. So having looked at a very tiny demo, here are some enticing bigger examples. And I've deliberately picked them from among, well, you saw on the title slide, thousands of projects we've done. I picked them for this list that fits on one slide to show the extremely high variation of situations, no matter what business you're in, that simulation can profitably handle in terms of contributing to the financial and service performance of your business. All of these are actual case studies we've done, and there's many more. And as I mentioned, these case studies, I certainly think, show the wide variety. For example, healthcare, business service, machine shop, small business, public transportation, restaurant, material handling. And another common one, a little bit related to this one, is warehousing. Simulation in the last few years has become very important to healthcare, and it's being, with all the supply chain strains of the pandemic years, it's become very important in warehousing and supply chain modeling. So that's a look at what simulation can do. There may very well be questions, and I'll turn it back to our nice host, Brian, for a Q&A.
Yep, thank you, Ed. And we did have a few questions come in throughout the presentation, and we'll get started with those. But please, if you have any questions for Ed, I recommend utilizing the Q&A feature at the bottom of your screen, and we can have Ed answer some questions that you might have had. But Ed, the first question that we had come in, it says you've mentioned several analysis methods, and it says, how do we choose which one to use?
Oh, good question. Let's go back a bit to that slide. The flippant answer, and a correct answer actually, is you ask a statistician. Any big simulation project certainly deserves to have a statistician available. If you were our client, it might be your statistician, it might be ours, it might be the two working together, and so forth. The statistician will help choose. Now, for example, confidence interval building and hypothesis testing are more appropriate when the number of alternatives to be considered is small. Now, a case where that arises might be, you have at the moment one proposed system design. And if you build the system according to that design, will it meet your performance metric objectives? So you model a system before you build it and run the simulation, look at your KPI like throughput, build a confidence interval for it. Does the confidence interval indicate that your performance, like jobs per hour, will be met? If not, thank goodness you found out now before you built the system. Conceptually, your system design is not yet adequate, and the computer screen is a very good, quick, inexpensive, non-painful way to find that out. Now, if you have a lot of independent things, especially if they're numeric, like number of workers or number of machines that you can vary, and you want to predict a KPI like throughput or average queue length that is also numeric, regression analysis works very well. If you want to analyze, are there going to be backup times in the system? Like that example of the campus bus service, when there's rush hours and traffic bottlenecks, time series analysis can be very helpful. Now, when you get into more alternatives, and I mentioned, 10, 20, 30, then you're likely to get into analysis of variance and design of experiments. So those are some of the basic thoughts that the statistician on the analysis team, and there'd better be one on the analysis team, would use to answer that question. How do you choose?
All right, thank you, Ed. Another question we had come in, what is an example of a maintenance policy choice?
Interesting one from a project just 2 months ago. A machine, very important, expensive one, vital to the process, has, unfortunately, some random breakdowns. And it also has, by specification of the manufacturer who provided the machine, and the machine will stay under warranty provided preventive maintenance is done on schedule. So for example, pick a number, a preventive maintenance, tear down, check everything, like an aircraft engine, for example, after 600 hours of operation. So that's standard, built-in, baked-in policy. After 550 hours of operation, the machine unfortunately has a random breakdown. Do we just fix it, run it another 50 hours, and then do the complete tear down, check everything? Or do we pull the scheduled maintenance ahead a little bit? And here, a little bit would be 50 hours, and do it all at once. That's a policy choice. Do we pull the scheduled maintenance ahead at all? And if so, we should pull it ahead only if the next scheduled maintenance is within the next X hours of operation, 20, 50, 75, and you'd put numbers in a simulation model, just like the different numbers that were in that little model I demonstrated. That would be an example of a maintenance policy choice. And one that came up last year in a warehouse, lights burn out in an aisle, ceiling lights, they're expensive and disruptive to replace. Someone has to get up on a ladder and the fork trucks can't go down that aisle. Do we just replace the burned out ones, or do we figure the ones in that aisle are still working or going to burn out soon? Do we sacrifice their remaining lifetime for simplicity of maintenance? That was an analogous example of another maintenance policy choice.
All right, thank you, Ed. Another question we have is, other than the examples that were given, are there some examples pertinent to warehousing specifically?
A great many of them concern, and simulation software has gotten very good at this, how do we do our order picking? There's various strategies of order picking to minimize the travel of our forklifts or our automatic guided vehicles. What should our routing disciplines be? How should the warehouse be laid out while it's still on a piece of paper, where the aisles are for the forklifts versus the aisles restricted to pedestrians? Very important for safety. So a simulation in terms of warehouse layout and order picking strategies has been very productive, not only in improving efficiency, but in improving safety. We don't want the forklifts hitting the workers.
Okay, thank you, Ed. I don't see any further questions coming in at this time. So with that, we'll close the Q&A session. So thank you, Ed, for answering those questions. If you think of any additional questions or you'd like to schedule up a meeting with us, please be sure to visit our website at www.pmcorp.com. Click on the resources tab or the contact us tab. Also, this video is being recorded. It will be uploaded to our YouTube channel sometime this week or early next week. If you want to review it, share the slides amongst your colleagues, we recommend you might do so. So if you want to search our YouTube channel, that's PMC Videos. That's capital PMC and videos with an S. There might be other topics of interest to you and your team. If you want to go check it out, subscribe to us, that'd be great. I'd like to thank everyone for your participation. If you think of any additional questions, you can contact us at the address now on your screen. And with that, we hope to see you at another one of our webinars. Thank you and have a great day.